Hello, dear students. Nice to meet you. Sorry that we are working in this, let's say, asynchronous mode. So I'm recording the information for you concerning the material of the lection that had to take place last Friday. Okay, so now we are going to talk a little bit about the next material that we have according to our schedule, and the material, like a presentation, is already uploaded to the Google Classroom. So if you don't mind, I will share my screen, and we are going directly to the Google Classroom. Where is it? I think here. Yes, this is our Google Classroom. So you see that the last message at the main window of Google Classroom. This is lection number 6. Let's correct it. Lection number 6. And there is already a presentation here. And so I will open this presentation and start my explanation concerning this. And after I will finish, the recording will be available by the link that will be also put it together, put it here. Okay, so we are going to start investigating a new method of a spectral analysis. Not only one, but some method of spectral analysis, like a spectral transform of Fourier, Hartley, and Walsh, and Hadamard, and some other methods, we already consider it. And I hope you know more or less how to deal with this method and how to apply them for the concrete task. I focus your attention that here we will use a discrete transform. So the original function that we will try to process, to analyze, will be a discrete function. So this is like a signal that is represented by its some number of its digital values. And this new method that we are going to consider now, it's called spectral transform at oriented basis. And this is comparably new method. Actually, it was invented at our department. That's why I would like to pay your attention that it could be a good possibility to use this method in your future project. For example, it could be your bachelor project. So if you will use this method in your bachelor project, for example, you will be ready to answer the question, what is the novelty of your project? What new method or what new approach did you propose? So the answer will be, we propose using a new mathematical approach, a new method for data processing. And because this is quite universal method, like all other spectral transform also, you could apply it for different signals with a different origin or different nature. So it doesn't matter, would it be signals of medical, biomedical, or maybe acoustic, or some electrical data, or data about power consumption, or whatever. So the main thing is that you have to take like a discrete sequence of some values of a physical parameter. It could be the data of measurement, the data of the calculation, or whatever. The main thing in the input of our method, we have to have some number of discrete values. After this, we will be able to apply our mathematics. This mathematics or another method, but anyway, from a mathematical point of view, starting from this moment when we obtain this time series or sequence of discrete values, there is no matter what is the origin of these values. Okay, let's start. if we will consider just in general view the spectral methods, the methods of spectral analysis, let's talk only about discrete methods for the moment. So we could use the common formula for any discrete transform without distinguishing them with each other. So without the recognizing which kind of method there is. So this is like a common formula. We have a finite interval of n capital discrete values, and we have y from nu. Nu is a Greek letter, like a variable for the spectrum. So y from nu, y capital, is the image or spectrum that is represented by its n discrete values. And this spectrum is calculated according to this formula by the known values, by the known original function or original signal that is marked as y small from x. And it is also represented by the same number of discrete values, n capital. So we have n discrete values in the input. This is our original function. And after some mathematical transformation, after applying some formula, we obtain its image. It's also represented by n discrete values. Here in the formula, S capital is a symbol of transform operator. So it depends of what kind of spectral transform do we use, but in general, in common formula, it is noted like just S, like a symbolic notation. And then we have a sum, and under the sign of sum, we have a original function y from x, and also we have a function of phi. Phi is a Greek letter that depends, here this function depends on two variables, nu and x. So this phi are the basic function, and depending of the kind of spectral transform, this basic function will be different. So it could be like a discrete exponential function for the well-known for you discrete Fourier transform. It could be another function like cosinus, cosine plus sine, like in Hartley transform, or whatever else. So depending on the type of a spectral method, it will be different basic function. So different basic functions automatically mean different transform. And now just to memorize a little bit, repetition from the previous material that we already studied. It's a Fourier basic function. So of course, I mean discrete Fourier transform, because I told you in a previous slide that we will consider for the moment only discrete method. So discrete Fourier transform, the basic function of a discrete Fourier transform is a discrete exponential function. And you did use this function in your second practical work. I think you remember this. In geometrical representation, this basic function could be represented by the different position of a vector, like here, and total number of different positions of this vector is n capital. So how many discrete values we have in original function? The same amount of basic function and the same amount of different placement of this basic function in the coordinate plane we have. And the formula for the discrete exponential function, in case if there is a method of discrete Fourier transform, is the well-known for you also formula that we did use in a second practical work. So this is a complex value because we have exponents, and in a power of exponents we have a complex j. And also we have two variables n and k that are integer at finite interval. So that takes a value from 0 till n capital minus 1. So totally we have n complex values. And each complex value could be defined by its real and imaginary part. So we have totally n plus n values in order to define all set of basic function of Fourier transform at the interval n. Okay, let's go further, and then there is another transform that is called Hartley transform. The difference between Hartley and Fourier transform is that Hartley transform has a basic function that are not complex, that are only real numbers. And how they achieved this? If we compare with the Fourier transform, we see that in Hartley method, basic function contains like a cosinus, cosine plus sine with the same arguments here in brackets. So if we would like to represent it in graphical form, so at the complex coordinate plane, we will have no real and imaginary part. Actually, there are here, but we don't use them in a formula for basic functions. There are only real numbers. In order to represent them correctly at this coordinate plane, we should to build some additional axis under the angle P/4, so it means 45 degrees. So this is the additional axis, and all positions of the vector of basic function could be represented by its projection to this axis that is traced under the angle 45 degrees. And as a result, we have twice less values in order to define all the set of basic function incomparable with the Fourier transform. So instead n plus n, like it was in Fourier transform, here in the case of Hartley transform, we have only n real numbers. And these real numbers will be from 0 till n minus 1, and each of them will indicate the concrete position, concrete placement of the vector of basic function at the coordinate plane. So here is this how the basic function could be calculated in Hartley methods, and let's go further. The next method is called Vilenkin and Christensen transform, that is named after two scientists. I already told you about these two scientists who invented this method together. And there is some interesting feature of this method, that is that actually this method is operating with a different counting system. It will be a counting system with the base m. You see, m is the base of counting system, and this m could be any simple integer number. So it could be 3, 4, not 4, it's not simple, 3, 5, 7, 11, and so on. And also there is some limitation in order to be to relevant use of this method. There is some limitation for the number of discrete values of original function. If in the case of Fourier and Hartley, it could be arbitrary number, any number of the discrete values of original function. So here in the method of Vilenkin-Christensen, it is necessary that we provide the number of discrete values as m in the power n, where n is our base of counting system, I will explain, and n is some integer positive value. So it could be 3 in the power 2 or in power 3 and so on, or 5 in some power. So it is necessary to provide this limitation for original function y from x. Okay, and the formula, the equation for the basic function in this case will be like here. And in the first look, it seems a little bit complicated because there is an exponent here and some quite complicated expression in the power of exponent. So we have complex character. We see that there is j here, so the basic functions are definitely complex. And also we have this sum. And how to calculate, how to understand what is this? Now we should remind that we are using another counting system. So we should represent the decimal numbers in this another counting system. And this representation could be expressed like here. So we have two variables. It's a Greek letter nu and x. X is variable that is variable of the original function y from x. So here this variable x, and the spectrum depends on the second variable nu. So there are two variables, and each of them should be represented in this counting system with the base m. And I will explain a little bit later how to do this, but actually it appears not so complicated, not much complicated, and the result is very, very successful and promising. Why? Because if we can visualize it in a geometrical interpretation, in a geometrical view, we have a coordinate complex plane with the real axis and imaginary axis, and the same expression for the basic function of Vilenkin-Christensen in acronym VKF, Vilenkin-Christensen function. And let's assume that our base of counting system will be m equal to 3. So there is a ternary counting system. Ternary means that the base of it is equal to 3. So we have on the geometrical interpretation, in geometrical view, we have only 3 different values. Even if the original function is represented by a very much number of values, for example, dozens or thousands or hundreds, the different values of basic function will be only 3. So the basic function, the vector of basic function will take a place consequently 1 or 2nd or 3rd, and no more other different places for this vector. Only 3 possible positions. And it becomes very, very easy to calculate because there is no need to operate with this huge amount of values like it was in Fourier or Hartley transform, because there in Fourier and Hartley we have n that could be dozen, 100,000, and in case of Fourier it was even n plus n, so it was twice more. And if we will compare this with 3, of course 3 is more preferable. So the disadvantages is to necessity to convert decimal numbers into another counting system that seems to be a little bit complicated, but in algorithmic form, no problem. But the advantage, a huge advantage, is that we obtain in a result only 3, or if we use ternary counting system, so only 3. If we will use another m, it will be another number, but still it's a very small number comparatively to dozen or hundreds. That's why this method is promising. And let's go further. Another method, symmetrical transform at finite interval, SFI shortly in acronym. This method was also invented at our department. That's why I would like to give you a knowledge about it, because you also can use it and you can estimate the advantages of this method in comparison with others. So the basic function of this symmetrical transform, actually they appeared as a combination of Hartley idea. So I'm just going to the Hartley transform to this slide. So the idea of Hartley was just to eliminate a complex unity, a complex character of basic function, and use this function cosinus, that is cosine plus sine. So this was the idea of Hartley. Then the idea of Vilenkin-Christensen transform is to use another counting system with the base m that leads to the significant decreasing of different placement of the basic functions at complex plane. So joining together these two ideas, we obtain a new method, a symmetrical transform at finite intervals. Here we use the Hartley idea of cosinus, cosine plus sine, and inside the bracket as a argument of these two functions, cosine and sine, we use the idea of Vilenkin and Christensen about the different base of counting systems. So here we use the representation of two variables, nu and x, in the counting system with the base m. Here we can use it. So Hartley idea gives us elimination of complex values, like it was in Fourier or Vilenkin Christensen. So in both this method, there are complex character of the basic function. And the common feature for Hartley and SFI, symmetrical transform at finite interval, is not complex values. The geometrical representation looks like very similar to Vilenkin and Christensen. So we also have m different values of basic functions. So m different position of the vector at coordinate axis. As in Hartley method, here we use the additional axis that is traced under the angle p/4, so it means 45 degrees. And we obtain two advantages. First one is only real values, and second one, very few number of different values. So there is a table that illustrates the comparison between different methods. So if we will have a look to the first horizontal row of this table, we will compare Fourier and Vilenkin-Christensen function. And the common feature for them both is the complex values. If we will have a look to the Hartley and SFI, we will have that they are real. Sorry, there is in Ukrainian here, but I will correct it for you. So the real and symmetrical. Symmetricity is also very important feature because it allows to use the same algorithm as for transforming from the original function to the spectrum and vice versa, from the spectrum to the original function. And if we will have a look to the first vertical column of this table, we will compare Fourier and Hartley. And the common feature for them both is n values of different functions. And the common feature for VKF, Vilenkin-Christensen, and symmetrical transform of at finite intervals is that they have only m values, that is much less than n capital. And we also use m-array counting system. Here I can correct, I think. Let's try. No, I will do it later. Okay. And then there is no finish. We can go further to improve our method and to make it more simple. In this case, we can take Hartley transform and modify it a little bit. And as a result, we will obtain oriented Hartley transform. So this is a modified version of the Hartley transform. We have traditional equation for the Hartley transform that is symmetrical. So the basic function is the same for the direct and inverse transform. It's a cosinus, cosine plus sine. And also we can modify it in order to obtain oriented Hartley. It will be non-symmetrical, so we will modify the basic function and obtain a different expression for the direct basic function and inverse basic function. Here then lower index D and R indicate the direct and inverse reverse transform. So for direct we have cosine plus A sine. The only difference with the traditional is this multiplier A. And this A could be calculated as tangents of a some angle alpha, where alpha, as you can see, is dependent on the value n, the number of discrete values of original function. So there is some new angle and a new multiplier like a tangent alpha that is put it here, and also in the equation for the reverse basic function. So reverse basic function will be cosine plus 1 over a. And there is only one small difference, but still there is difference between basic function of direct and inverse transform. And if we would have a look to the geometric view, so there's this additional axis that was in traditional Hartley transform traced under the angle 45 degrees, here will be traced under the new angle, under the angle alpha that could be not equal to 45 transform. And there is why this method is called oriented Hartley transform. So we just rotate this by changing the angle of the additional axis, so it changes, and thus the transform to the whole is oriented. Okay, and this alpha now it is not more equal to p over 4, and it also could not be equal. There are some restriction. It could not be equal to p over 2 plus pk for different k, and also pk. So it could not take a place of a vertical and horizontal axis because there are coordinating axes. All other position could be, there are allowable. Here alpha is equal to 2pi over n. And this trick helps to decrease the values of basic function in comparison with traditional Hartley transform. For traditional Hartley transform, we had n values of basic function. For oriented Hartley transform, we have significantly decreased values, twice decreased values. So instead n, we have n over 2 or n plus 1 over 2, depending on what is n. Is it a pair or non-pair value? So this trick, orientation of the additional angle, allows to decrease the different values, number of different values of basic function, and thus to simplify the calculation, of course. And also we can do the same with the spectral transform at finite intervals that was in one of the previous slides, SFI transform. And also we can apply this trick with orientation to this transform. So traditionally, SFI transform was also symmetrical like a Hartley transform in its traditional form. It was like this expression, a basic function was defined by the expression of cosine plus sine or cosinus from the argument that depends of the m that is the base of counting system, and it is symmetrical, so there is the same basic function for the direct and reverse transform. But if we will apply orientation, we will obtain a new method, and actually we do the same like it was in the previous slide for Hartley, orientation of Hartley transform. We put a multiplier a in the formula for the direct basic function and 1 over a in a formula for the inverse basic function. Thus, our transform that now is called OB transform. OB means oriented basis, the transform at oriented basis, or shortly OB transform, is non-symmetrical. So it has a special formula for the direct basic function and for the reverse basic function. The multiplier A is also defined as a tangent of alpha, but the alpha is different than in oriented Hartley transform. There it was 2pi over n capital, and here we have 2pi over m, where m is the base of our counting system and should be a simple positive integer number. So we could use this. And because in this case we obtain non-symmetrical method, The question is, could we replace this direct and inverse basic function and change the places of it? Is it possible to use the inverse basic function for the direct transform and direct discrete function for the inverse transform? And the answer is yes, it's possible, and it means that there are two modifications, at least for the moment, there are two modifications of this transform that is called OB1 and OB2 transform. And here the table illustrates this two modification, OB1 and OB2. We have original functions that could be calculated by the spectrum. Here in first case, we have a spectrum Y capital with the upper index 1 in a bracket, and here Y with the upper index 2. So this is like a two different spectrum of the same original function, because original function Y from X is the same without any indexes. And here the second horizontal row in a table, there is a formula of direct transform. Direct transform, I remind you, this is a way how to calculate the spectrum or image. In our case, this image is Y capital from nu, here and here, by the known original function. So the original function is the same, but the spectrums are different. Y1 and Y2. The difference between these two formulas is here under the sum is a phi d, so basic function of direct transform here, and phi r, basic function of the inverse transform here. So the basic function of direct transform is here phi d and here phi r. And the basic function of inverse transform are just change their places. So when we use phi d for the direct transform, then we use phi r for the inverse transform, and vice versa. So there are two modifications of OB1 and OB2 transform. Moreover, there is no, again, there is not an the end. We also can create more modification of this method. We can create a different OB transforms because, as you know, this method is oriented method. So we use additional axes that is traced under some angle, not 45 grade more, but in some on some angle alpha. Alpha could be defined as 2 pi over m, and if you put different I here, then we will obtain a different angles. And if we will trace our additional axis by on these different angles, we will obtain a different methods. So the first way to get a modification is exchange of direct and inverse basic function, resulting OB1 and OB2. And the second way is to changing the orientation angle. That will result to different m-1 values. So we can use different amount of the angle, m-1. So totally we will obtain 2 multiplied by m-1 different modification of the transform, or 2 m-1 different transforms. So this method is very, very different and could be changed. This or that modification could be changed for concrete task. And then let's go further. Let's have a look what happens if we will choose the base of counting system m equal to 3. And it means that original function should be defined by their 3 in some power values. For example, if we will take 3 in a square, 3 in a power 2, so totally 9 values of original function. Of course, there is no real situation because it's very, very simple. In real task, there is more interesting to deal with a more amount of discrete values, and the real-time series that are to be analyzed in a practice, actually they contain much more than 9 values. It could be some dozens or some hundreds, I already told you. But we will consider very simple case in order to understand everything in details. If we will understand this very simple case, of course, we could consider also more complicated case and also deal with this. But it is very extremely important to understand how to deal with the simple case, but understand it absolutely clearly in detail. So let's do it. We take the interval 3 in the power 2, so 9 discrete values. And also in this case, we could use different, actually 2 different values of the orientation angle, because the common formula for this angle alpha is equal to 2pi over 3. And this I could take values 1 and 2, because it's from 1 till m minus 1. Our m equal to 3, so m minus 1 it's 2. So it means that I could take only 2 possible values, 1 and 2, 1 or 2. So there are 2 possible angles, 2p over 3 and 4p over 3. There are 2 modifications, and also we can change the places of the direct and inverse basic function, obtaining OB1 and OB2 modifications. So totally we could obtain 4 transforms. 2 multiplied by m minus 1, m equal to 3, so 3 minus 1 is 2, 2 multiplied by 2 is equal to 4. So we have OB1 and OB2 for one angle, and OB3 and OB4 for the second angle. And the beautiful thing, let's say, the most beautiful thing here that the matrices of basic function, and the basic function, of course, could be represented in a form of matrix. This matrix will be square, the same amount of the vertical columns and the horizontal rows. In this case, we have 3 in the power 2, so totally 9 values. That means the dimension of matrix will be 9 by 9. So the numeration of the vertical columns will correspond to the values to variable x that takes the values from 0 till 8, totally 9 numbers, and the numeration of the horizontal axis will correspond to the value to variable nu that takes a value from 0 till 8, totally 9 values also. So we have the matrix 9 by 9, and if we will calculate according to the formulas of basic function all these values, so we will obtain 2 these matrices. For the direct and for the inverse transform, both matrices are the same dimension, 9 by 9. Both of them are symmetrical, so if you will compare the values above the main diagonal and below the main diagonal, you will see that they are placed symmetrically here and here also. So these are 2 matrices for the first angle, 2p over 3, and you see that the beautiful thing I told you, that the values of element are very, very simple. We have only 1 and minus 2 here, which is quite simple, no some complicated values. And even here we have about 33% of zeros, and the other elements take the values 1 and minus 1. So it's very easy to operate with this matrix, but these are only for the case if we will take m equal to 3. So it's important, because if we will select another values of m, for example, 5, 7, and so on, so the matrices will not be so simple. So only for m equal to 3, it's like a very favorable case. And here you can see the process of the calculation of basic functions. So we have the formula for the phi d, so there is a basic function for direct transform. Here there is a formula, and inside the formula within you have nu and x, that don't forget, they should be represented in counting system with the base 3. And here in the table you can see the representation of decimal numbers x and y from 0 till 8, because for this example we have only values from 0 till 8. So for each of them there is a representation in a ternary system. Ternary means a counting system with the base 3. Okay, so 0 represents by 2 zeros. This is like a 2 positions in ternary counting system. Then 1, 0, 0. Then 2, 0, 2. 3, 1, 0. 4, 1, 1, and so on. This is similar to the binary system, but in binary system we have only 2 possible values of each digit, 1 and 0. Here in ternary system we have 3 possible values of each digit, 0, 1, and 2. So here there is a representation of the decimal numbers from 0 till 8 by 2 digits of ternary system. And here, according to this, we can put all of this here. So we have x1, x2, new 1, new 2, and then we can put it here in a formula, and we will obtain the different values of the basic functions that then could be placed in the matrix that I told you here, here, and here. So there is an illustration of how to calculate couple values of this function to put it in the matrix of the direct basic function. But the same could be for the inverse basic function, and so on. You can check yourself, and you can try to calculate it just to understand how it works, how this formula is calculated using this ternary counting system. And also there is one more advantage, that is the existence of the recurrent form of basic function, like it was for the Hadamard transform, when we were able to construct any dimension of the matrix, of Hadamard matrix, by the elementary matrix. So we can enlarge more and more the dimension of matrix, and also this mechanism is also working here. We have an elementary matrix like 3 by 3. I remind you that we selected m equal to 3, and we decided to work with the ternary counting system, so our elementary matrix will have a dimension 3 by 3. And this matrix has a logical structure, like you have the same values in a first horizontal row and a first vertical column. This value equal to A0. Then we have in a second row, we have A1, A2, and the third row, they are changing their place, A2, A1. A0, A1, and A2 have the concrete values. It's 1, -2, and 1. So we can put instead A0, A1, and A2 their numbers and obtain the matrix, elementary matrix 3 by 3. Then, using this elementary matrix, we could construct the next dimension. It's the matrix 3 in a square 2, so 9 by 9. And the logics of this construction will be the same. So instead A0, here in the matrix of the next dimension, we will put this elementary matrix FD3. So we have FD3 here, all the element of the first horizontal row and the first vertical column. And the rest values of the second horizontal row, we could calculate it by using the mathematical operation by module 3, but this operation is applied only for the index. So here instead 3, we put 3 plus 1, but this plus is by module 3. You should remember that we do already mathematical operation by module 2, for example, where 1 plus 1 was equal to 0, and 0 plus 1 equal to 1, and so on. Here there is the same, but this is an addition by module 3. So 3 plus 1 should be 4 if it would be usual addition, but in case of addition by module 3, we obtain it like equal to 2, because in ternary system we have 0, 1, 2, and then again 0, 1, 2. So you could check yourself and understand how it works. And here you can see the detailed explanation how to do this. So fd3 plus 1 by module 3, you should add this one to every lower index of every element of the original our elementary matrix. So A0 plus 1, so 0 plus 1 is 1. 1 plus 1 is 2, and 2 plus 1 is 0, because we are dealing with ternary system. So here there is another matrix, also with the dimension 3 by 3, where the elements are mixed. In comparison with elementary matrix, there are the same 3 elements, but they are mixed with this way. And the second element of this 9 by 9 matrix is 3 plus 2 in the lower index. So here there is an explanation how to do this. And again, we obtain the matrix 3 by 3 that is different than the previous one and then elementary matrix, but still they consist only of these 3 the same values, A0, A1, and A2, that we know exactly what they are. So after putting all this very accurately and very precisely, we will obtain the matrix with the dimension 9 by 9, and that was already presented, and here just an explanation how to do this. The same recurrent algorithm will be work for the enlarging the dimension of the matrix for the further enlarging. So 9 by 9 matrix will be used for the construction of matrix 27 by 27, then 81 by 81, and so the same logics of recurrent form. And this is a good advantage, because this is like a method that could be very easy put it into the algorithm in a computer during a programmation. So there is a very promising method of spectral transform, OB transform, or transform at oriented basis. And here you can see also the table that illustrates that there are some partial cases of this transform that coincide with the well-known transform. For example, if we will take A equal to 1, A is a multiplier in the expression of the basic function, so we will obtain the function, basic function of symmetrical transform SFI, where discrete direct basic function are equal to the inverse basic function. Then another partial case, if we will take m equal to 2, so we will not use with a ternary counting system, but with binary counting system, and still a equal to 1, we will just obtain Walsh function that you already know. There is a practical task number 3 that I hope you already finished. So also the Walsh function is a partial case of OB transform for the condition m equal to 2. And if we will take n equal to 1 and a equal to 1, we will obtain the traditional Hartley basic function. So the Hartley transform, it's also the partial case of OB transform. And here you can see a very simple example of how to apply this transform. So let's take original function like a function that is represented by its 9 values, 3 in the power 2. So we have an interval n 3 in the power 2 equal to 9. And we will have only one value of orientation angle, alpha equal to 2p over 3. And our task is to calculate a spectrum. How to do this? The most simple way is to do this in matrix form. Here there is an equation for the direct transform. Direct transform means that we know original function y small from x, and we are calculating y capital from nu. And here we should use the matrix of the direct basic function phi d, and here there is a calculation. We have 1 over n as a multiplier before the matrix. Our n is equal to 9, so 1 over 9 here. Then the matrix 9 over 9 that was already calculated above. And then we have an original function that is represented in a form of a vertical matrix column. And then just very simple calculation. So we just multiply first horizontal axis by this column, then second row by this column, and so on. And we will obtain a result. So the image spectrum will be like here. And you can agree that it is not difficult. It's quite easy to calculate because of this very simple matrix of the basic function. So only for this method, in comparison with others that we already considered, there is very simple calculation. That's why it is very promising. And in order to get back and to check ourselves, to know, to be sure that we did everything correctly, we will just use an inverse transform, just taking this calculated spectrum, and then using the matrix of the inverse transform and obtaining the original function. In this case, we use another matrix. So here it was a matrix that contains 1 and minus 2, and here a matrix that contains 1, minus 1, and 0. And we do the same without the multiplier 1 over n. Here is the equation in a matrix form. To calculate original function, we should use the matrix of the inverse basic function and multiply it by the spectrum that we calculated before. So we do this again, the same matrix calculation, and we will obtain the same original function that it was in the beginning of the example. So 0, 1, 2, and so on till 8. Here there is some example of, not example, but detailed calculation of matrix. Okay, that's it for this method. So thank you very much for the attention. I hope it will be useful for you, and you will get a more knowledge about this new method. If you will still have some question, please address this question to me. I would be happy to answer and to help you with understanding. And of course, this recording will be uploaded to YouTube, and you will obtain the link to see it and to investigate this new method. And good luck with this. Thank you very much again, and bye.